This is Lab 5, Magnetic Braking with Faraday. In this lab, we record the time it takes for a bar magnet to fall through a conductive tube of aluminum foil. The interaction of the magnet and tube of foil is modeled computationally. Then the observed time from the experiment is compared to the predictions of the computational model. The fundamental physics principles used in this lab include magnetic field, induced current, and Faraday's law. I used a stopwatch to get the time it takes for the magnet to fall through the tube. My final average for the experiment was 1.21 seconds. For the computational model, it creates a tube of aluminum foil as a series of rings stacked along the y-axis. The computational model requires the magnetic moment, which I reused from Lab 3. The value of that would be 2.79. And to calculate it, I used the equation k equals 1 times 10 to the negative 7th times 2 mu. It also requires the length, thickness, and inner radius of the tube, and for that I got 0.3 meters, 0.01 meters, and 0.025 meters respectively. For the computational model, a function to calculate the magnetic field at position r relative to a bar magnet and a function to calculate the magnetic flux were both necessary. The output of the computational model includes a cylinder which represents the aluminum foil and also the magnet dropping through it. Another output of the computational model is the velocity versus time graph. This graph shows the velocity versus time for the magnet as it drops, and the time predicted by the model is 0.656 seconds. So comparing the two times, it took 1.21 seconds during the experiment, and the predicted time was 0.65 seconds. This is not expected because the experimental magnet should go through the tube faster than the magnet in the computational model. This is because the magnetic force will be larger in the computational model compared to the magnetic force in real life. Some reasons the predicted time was faster than the observed time include human error calculating the observed time and human error calculating the magnetic moment. To conclude, if the resistivity of the conductor were reduced as close as possible to zero, it would take more time for the magnet to fall through the tube due to an increase in the induced current. If holes or slots were cut into the tube, it would take less time for the magnet to fall through the tube due to a decrease in the magnetic field. Using right-hand rule, we can see that the red represents the clockwise current and the blue represents the counterclockwise current in the computational model. Finally, if you flip the magnet around, the dynamics of the system does not change.